Now, in this last lecture, we'll look at a few more goodness of fit tests. So, the first one we'll discuss is the likelihood ratio test. The likelihood ratio test compares H0 to a parameter dependent alternative, H1, which includes H0 as a special case. The two hypotheses are defined through PDFs. F for x given theta and F for x given theta 0. The theta 0 some subset of theta. The test statistic is the likelihood ratio, which will denote by lambda. So this is the ratio of the likelihood of H0 and the likelihood of H1, where the parameters are chosen such that they maximize the likelihoods for the given observations. So this is given by an expression, the supremum of the likelihoods. So matter of fact, ratio of the supremums of the two likelihoods, or equivalently in terms of logarithms, so difference of the supremums of the log likelihoods. So if theta 0 is a fixed value, then this basically becomes so as an example, let's look at the likelihood ratio test for a Poisson count. So we say H0 predicts mu0 equals 10 decays in 1 hour. Observed number of decays is 8. So the likelihood to observe 8 for the Poisson distribution is the likelihood is maximal for mu equals 8, and in that case it is so this implies that the likelihood ratio The probability to observe a ratio smaller than or equal to 0.807 is the likelihood ratio test in this general form is useful to discriminate between a specific and a more general hypothesis. To apply it as a goodness of fit test, we have to histogram the data. So let's look at the likelihood ratio test. For histograms. The test variable is the ratio of the likelihood for the hypothesis that the bin content is predicted by H0 and the likelihood for the hypothesis that maximizes the likelihood for a given sample. So if you are looking at a bin with content D, prediction T, PDF given as F for D given T, lambda is basically given as F for D given T, F for D given D. Since the likelihood is maximal at T equals to D. For the histogram, we have to multiply the ratios of the B individual bins. But if we change to log likelihoods and use it as a test statistic, we can instead have sums instead of products. If the bin content follows Poisson statistics, and by appropriately replacing the distribution function, we get which basically simplifies as di minus ti plus di times log of ti by di. The distribution of the test statistic, which we have denoted by capital V here, is not universal. It is not independent of the distribution to be tested, as in the case of chi-square. It has to be determined by a Monte Carlo simulation. In case the parameters of the prediction have been adjusted to data, parameter adjustment has to be included in the simulation. Asymptotically, as n goes to infinity, the test statistic approaches minus chi-square by 2. This can be seen in the expansion of logarithm. So if we introduce xi equals di minus ti by ti, we can basically rewrite v is the sum over ti xi minus ti times 1 plus xi, log of 1 plus xi. So we can approximate this. And using just the first two terms of the log expansion, take ti on the outside, it becomes xi minus 1 plus xi times xi minus half xi square. So this can further be approximated as if you're only keeping term to the x square part, this basically becomes minus half times sum from 1 to b of di minus ti square by ti. Thus, minus twice of v is distributed according to a chi-square distribution with capital B degrees of freedom. But then in such a case, we may also directly use the chi-square test. Now, if the prediction is normalized to the data, we have to replace the Poisson distribution with a multinomial distribution. And in that case, the test statistic is simply given like this. In this case, V approaches asymptotically the chi-square distribution with b minus 1 degrees of freedom. Next, let's look at something different. Just the Kolmogorov-Smirnov test. So the subdivision of a sample into intervals is arbitrary and thus subjective. Some experimenters use the freedom to choose histogram bins such that the data agree as well as possible with the theoretical description in which they believe. And this problem is excluded in binning-free tests, which have the additional advantage that they are also applicable to small samples. So the Kolmogorov-Smirnov test compares the distribution function f0x is given as an integral from minus infinity to x of f0x dx with the corresponding experimental quantity s of x, which is the number of observations with xi less than x divided by the total number of observations and the test statistic is the maximum difference between the two functions. So it's the supremum of the modulus of fx minus sx. It's also written as the supremum of d plus d minus. So d plus and d minus denote the maximum and the minimum or in other words, it's more appropriate to call them the maximum positive and the maximum negative differences. Now, Sx is a step function an experimental approximation of the distribution function and is called the empirical distribution function. Or EDF for short. To calculate Sx, we sort all n elements in ascending order of their values and add 1 by n at each location xi to Sx. So S of xi is the fraction of observations with x values less or equal to xi. S of xi would be I by n and S of xn would be 1. Just like in the chi-square test, we can determine the expected distribution of the test statistic D, which will depend on capital N and transform the experimental value into a p-value. The Kolmogorov-Smirnov test emphasizes more the center of the distribution than the tails, because there the distribution function is tied to the values 0 and 1 and thus is little sensitive to deviations at the borders. Since it is based on the distribution function, deviations are integrated over a certain range. Therefore, it is not very sensitive to deviations which are localized in a narrow region. There of course exists other EDF tests which in most situations are more effective than the simple Kolmogorov-Smirnov test. Now, there are a number of tests which belong to the Kolmogorov-Smirnov and Kramer-von Mises families. We have what is called the Kuiper test, in which one uses as the test statistic is the sum d plus thus d minus of the two deviations of the empirical distribution function s from f. And this quantity is designed for distributions on the circle. These are distributions where the beginning and the end of the distributed quantity are arbitrary, like the distribution of the azimuthal angle, which can be presented with equal justification in all intervals. The tests of the Kramer-von Mises family are based on the quadratic difference between f and s. So in the simple case, the test statistic is denoted as w square, which is an integral from minus infinity to plus infinity of the squared difference of fx and sx. And a number of situations also have what is called the Anderson-Darling test, with the test statistic given as a square, which is n times this integral, so squared difference of sx minus fx divided by fx times 1 minus fx. We also have the test of Watson, where the test statistic is given by u times, we integrate over the difference of sx minus fx minus the result of that integration, and we take a square of the whole thing. And these last two, Anderson-Darling and Watson, are superior to Kolmogorov-Smirnov in a number of cases. The test of Anderson basically emphasizes the tails of the distribution, while Watson's test has been developed for distributions on the circle. Now, the formulas above look quite complicated at first sight, but they simplify when we perform a probability integral transformation. This stands for a simple transformation of the variate x into a variate z. And this new variate z is uniformly distributed in the interval 0, 1. And it has a simple distribution function. With this transformed step distribution of the sample, we can write a square equals n times integral from minus infinity to plus infinity star z minus a square So as a final example, we'll discuss what is known as Neimann's smooth test. This is different from those discussed so far in that it parameterizes the alternative hypothesis. So this was introduced by Neimann as an alternative to the chi-square test, in that it is insensitive to deviations from H0, which are positive or negative in several consecutive bins. So Neimann insisted that in hypothesis testing, the investigator has to bear in mind which departures from H0 are possible, and thus to fix partially the PDF of the alternative. The test is called smooth because, contrary to the chi-square test, the alternative hypothesis approaches H0 smoothly for vanishing parameter values. The hypothesis under test H0 is again that the sample after the probability integral transformation follows a uniform distribution. The smooth test excludes alternative distributions of the form gk of z sum over I equals 0 to k theta I z. Theta I are the parameters and pi I z are the modified orthogonal Legendre polynomials. And normalized to the interval from 0 to 1, and symmetric or antisymmetric with respect to z equals half. So we basically have so in this case, pi of x is the Legendre polynomial in the usual form. The first parameter, theta 0, is fixed. And other theta I are restricted such that g of gk is positive. Then the user has to choose the parameter k, which limits the degrees of the polynomials. If the alternative hypothesis is suspected to contain narrow structures, we have to admit large k. The test with k equals 1 rejects a linear contribution. The one with k equals 2 rejects a quadratic component and additionally a quadratic component and so on. Obviously the null hypothesis H0 corresponds to theta 1 equals all the way up to theta k equals 0, or Equivalently, sum over theta I square from I equals 1 to k 0. So you have to look for a test statistic which increases with the value of this sum. So for a sample of size n, the test statistic proposed by Nyman is given as rk square is 1 by n times the sum over I equals 1 to k ti square. Ti is nothing but sum from j equals 1 to n of the pi i's as a function of zj's. This choice is plausible because a large absolute value of ti is due to a strong contribution of the polynomial pi I to the observed distribution, and thus also to a large value of theta I square. While under h0, we have for I greater than equal to 1, the expectation of ti is n times the expectation of pi I as a function of z equals to 0, because this comes from a property of the pi I is that it integral from 0 to 1 makes them vanish. Asymptotically, n goes to infinity. Under h0, rk square follows a chi-square distribution with k degrees of freedom. And this is a consequence of the orthonormality of the polynomials and the central limit theorem. And we have a variance of ti and as a sum of n random variables, the statistic is normally distributed for large n with expectation equal to 0 and variance equal to 1. And due to the orthogonality of the pi i's, the ti i's are uncorrelated. Small n, the distribution of the test statistic, has to be obtained by a Monte Carlo simulation. The smooth test is in most cases superior to the chi-square test, and this can be understood in the following way. The smooth test scrutinizes not only for structures of a fixed frequency, but for all frequencies up to k, while chi-square test, with number of bins much larger than 1, is rather insensitive to low frequency variations. Now, in the literature, there are many more goodness of fit tests that are often discussed, and each of them have their respective merits, but we'll continue our discussion up to this point. And we'll wrap up this series with this video. So the next steps from here could be a closer examination of the same concepts that we have covered so far, but using software tools, using code packages to explicitly study how numerical computations are done, Monte Carlo estimations, Monte Carlo simulations. And now we can visualize the various concepts that have been covered so far using different kind of graphs. Now, another possible direction in which an intermediate or an advanced level discussion can go is towards the field of statistical learning. And that would also bring into picture the concept of machine learning and various subjects that come under that umbrella. But that is beyond the scope of this discussion. So this is where we'll wrap up the lecture series.